Today, we're going to talk about implicit differentiation. Implicit differentiation is used when the variable we're differentiating doesn't agree with the variable it's being differentiated with respect to. Here, we're differentiating x with respect to x, so we can just use a normal derivative rules and say that this is 2x by the power rule. But here, we're trying to differentiate y with x, so it's not that simple. To implicitly differentiate, we're going to assume that y is a function of x and use the chain rule. So if I let f equal y squared, then here we're basically just trying to find df dx. So f is a function of y, so I want to differentiate f with respect to y. But if I leave it like this, these aren't the same. So here I have to multiply by dy over dx so that the dy's will cancel and we have df dx equals df dx. And remember, this is exactly the same as the chain rule. Now let's actually go find this. If I want to find df dy, we're just going to differentiate f with respect to y, and since the variables agree, we can just use the power rule to say that is 2y. Now we need to find dy dx. But we don't actually know what y is, we just assume it's some general function of x. Since we don't know how to express dy dx in terms of x, we just leave it as dy dx. And this is our answer. The reason it's called implicit differentiation is because this here is just an implicit derivative of y. So we don't actually know what dy dx is, but we do know that we have to multiply by it if we want this to be true. So implicit differentiation is the same thing as a chain rule, but we don't know what the inner function is. So if you're ever asked to find dy dx with implicit differentiation, you'll have an equation. And that means after the calculus, we're going to use algebra to solve for dy dx. Like in this example. So we're given that x e to the x minus y cubed equals 2, and we're going to find dy dx. So the first thing I'm going to do is we're going to differentiate both sides with respect to x. And we can apply the derivative term by term. By the power rule, the derivative of x e to the x is first d second plus second d first minus the derivative with respect to x of y cubed. And this equals the derivative of 2, and from the constant rule, we know that this is 0. From this, we know that x e to the x plus e to the x equals the derivative with respect to x of y cubed. Remember, if we want to find the derivative with respect to x, this is df dy times dy dx. By the power rule, df dy is 3y squared. And remember, we don't know what y is, so we leave it as dy dx. Now I want to substitute this back into our equation, like so. And all I have to do now is divide both sides by 3y squared. And this is our final answer. And another reason why this is called an implicit derivative is because it's in terms of both x and y. If we had a situation where the variables agreed, then we would have dy dx only in terms of x, making this an explicit derivative. But here, we have to use our function to describe the derivative of our function. Let's finish off the video with another example. So we're given that x squared plus y squared equals 1, and we're asked to find dy dx. So we have our equation, and the first thing you always do is differentiate both sides with respect to x. We split the derivative term by term. By the power rule, the derivative of x squared is 2x. By the constant rule, the derivative of 1 is 0. And finding the derivative with respect to x of y squared, by the power rule, we have df dy is 2y. And since we don't actually know what y is, we just leave dy dx. Now I'm going to substitute and subtract 2x from both sides, like so. And lastly, all I have to do is divide by 2y on both sides. And that yields that dy dx equals negative x over y. Let's geometrically think about why dy dx has to be implicit here. Recall that this isn't a function, because if I have an x value here and I'm asked to find the height at that x value, I could either tell you here or I could tell you here, which makes it not a function. Similarly, if I was asked to find the derivative at this x-coordinate, I could either say this tangent line or this tangent line. The derivative can't be a function either. And this goes back to the first video of the chapter with the dependency of the function and the derivative. So the function has to exist for the derivative to exist. And if the function doesn't exist, then the derivative doesn't exist, or it has to be implicit. We can also find further derivatives with implicit differentiation. If I want to find the second derivative here, that's the same thing as taking the derivative of the derivative, like so, which is the same thing as the derivative with respect to x of minus x over y. To find this, we're going to have to use the quotient rule. The quotient rule is bottom times d top minus top d bottom. And remember that d bottom is dy dx because we don't actually know what y is. And all over y squared. And that simplifies to this. If you look up here, we found dy dx when we found the first derivative, so we can substitute that in for here, like so. Which reduces to this, and this is our implicit second derivative. And that's how you do implicit differentiation.